Hey everybody, and welcome to another Jamovi tutorial. In this tutorial, we are going to explore a module, an add-on module that I haven't explored yet. It's called JEVA, and I'll explain how you get all of that module stuff into your Jamovi in just 1 second. Now, as I have mentioned in a previous video that came out sometime on the channel in the last, I don't know, month or so, I am using a not super updated version, 2.3.19. It's 0.2, the last 0.21, 2.3.21, because I did some bug fixes, and so it wasn't their last 2.3 update. But I'm just going to wait for the next big update to update my Jamovi. So I am, as I said, using a slightly not updated version, and hopefully I don't encounter any of the bugs that were fixed in this video. Okay, so JEVA. What the hell is JEVA? Okay, perfect question. So as you can see here, I've got all the modules up at the top, and here we are with JEVA there. I haven't added a fun little icon yet, but how you add it is you go up to, and then there's a lot of overlap here with the UI, but you go up to modules, and you click on that plus button, and you can go and you can see this is the list of all of them. And if you go through, and you can go to Jamovi library or manage installed. They open up the same little dialog box. So manage installed, since I already have it open, and you want to go to available. And you can see I've already had it pulled up because I've been reading about it and looking into it. And I realized that I hadn't made a video about it. And I was like, I thought I did all of the modules that I know how to do. I don't know how to do all statistics, and I'm working on it, but I don't know how to do all statistics. So I was going through the module list to see what videos that I hadn't done yet. And this one popped out to me. And I'm like, I know how to do t-tests, but this is a different kind of t-test. This is a new way, or not a new way, essentially, but sort of moving away from the traditional frequentist p-value interpretation. And according to its proponents, it's an easier, more intuitive way to understand how to do statistics at the frequentist level, or at least the analysis used for various various things like t-tests or ANOVAs or all of the kinds of experiments that we do generally as scientists or data analysts and that kind of thing. So this is a relatively new package. It's an R package developed by Peter Kahusak. I don't know if I'm saying that right, so Peter, I apologize. And this was a package that he created for his book, Evidence-Based Statistics. If you click on this link, it'll take you to the Amazon page where you can purchase the book or look through a sample or something like that. I looked through it briefly. Let's see. It is, ebook is $91 US, and hardcover is anywhere between $88 and $99 US. I'm sure there are other ways to get this book. I don't know if it's got a used market yet. Ooh, yeah, the used market is about the same. Oh boy. All right. Well, oh yeah, there you go. Used is 88. Yeah, okay. So that's not on the screen. Anyways, evidence-based statistics. If you want to learn more from Peter about how to do this, I'm going to show you the t-test module. There are or analysis within this module, and you can extrapolate how to do the other ones from there, with resources online. I will link a few different things in the description below, so you can find the book, you can find the paper on the R package, which is what this is. And you can explore it from there if this is something that you want to explore in your teaching or in your statistical learning. Again, not super versed in this, but I can explore and explain what it is you're seeing here and whether or not it's something that is useful to you as a teacher of statistics or a learner of statistics. So when you come to this available screen here, there'll be a button. You can see I already have it installed. There'll be a button that says, install. You click on that, it'll install it, and we'll go up here and close that. And again, you can get it from your top bar, or you can go find it in your list here. Where was JEVA? JEVA. I wish this was in alphabet. Oh, there it is. JEVA, and there's the list of all of them, or you can click on JEVA here where it's actually a little bit easier because things are divided by the type of test they are. So like I said, I am going to do an independent samples t-test. And when you open the independent samples t-test, this is what pops up. It is basically already populated with the tables that you need and this lovely bit of explanatory text. So Peter, well done on this. I love modules that have explanatory text because it really helps the learner and the teacher explore the data and the analysis together. So I love that. That's on by default. And by default, down here is where the explanation goes. And so you already have interpreting support S, which is the statistic for the log likelihood ratio, the log LR. So the log value of the likelihood ratio. Now, what is the likelihood ratio? The likelihood ratio, as you can see here, LR, the likelihood ratio, assesses the goodness of fit in two competing statistical models based on the ratio of likelihood, so how likely they are. Specifically trying to maximize one over the entire model space. by imposing a constraint. And that constraint is usually the null hypothesis. And here you can see we've got HO and HA, we've got the null hypothesis, and we've got the alternative hypothesis as HA. And by default, the the HO is 0, right? Because in a t-test, if you're familiar with frequentist statistics, you would say that the null hypothesis is that there are no differences between the two groups. So that's what the likelihood ratio constraint is. And so if the null hypothesis is supported by the observed data, the two likelihoods should not differ. And so the ratio, the log likelihood ratio, LR, is 1, right? So if the two numbers, the numerator and the denominator, are the same, then the ratio quotient is going to be 1 and therefore support for the null hypothesis, okay? So the observed data is no different from the constraint that you're putting on the model, okay? And so as you can see here in this lovely handy dandy table, we've got a 1 referencing no evidence either way. And I love the framing of this because the null hypothesis is assumed to be the state of the world when you jump into analysis, right? And that's the same thing for null hypothesis statistical testing that relies here on this p-value, right? And the p here, as indicated by Peter, the creator of this package, is there to show you how null hypothesis statistical testing would be used in this situation compared to using the log likelihood ratio test. And so, like I said, if we've got 1, so the numerator and the denominator are the same value, right? The ratio of the log likelihood, no evidence either way. When you get a null hypothesis result, you don't just say, oh, well, I guess my difference is done. Time to pack it up and pack it in. I'm done with science. Gotten plenty of null results in the past, and you can't say, oh, okay, well, there's no difference. You really have to go back to either your theory or your methodology and find out whether or not it really is the null hypothesis is the state of the world by continuing your experimentation, right? So no evidence either way sort of spurs you, I can never remember the difference there, tells you that more searching is necessary here. So I love that idea. Well done at the phrasing. I mean, it's just basic phrasing, and I'm just trying to sort of explain the phrasing. Okay. And so as the log likelihood ratio gets bigger and bigger, we get weak evidence, we get moderate evidence, we get strong evidence extremely. And then if it's a really big value, more than 1,000 to 1, if it's a really, really big value, you can see that this is 10 to the 6th power here, more than 1,000,000 to 1. And your S will increase proportionately there as well. Okay, so let's talk about, and it's apologies if you can hear my chair there. So let's talk about setting up this in Jamovi, right? Because Jamovi is the graphical user interface for the R package. So if you're not comfortable with using the coding language of R, Jamovi offers you the next best thing if you want to explore evidence-based statistics from this creator here. So here I actually brought in the wrong one. Well, that was the clean one. Here is the not clean one. That's not what I wanted. That's full screen. Let's not do full screen. Thank you. Option. That's what we wanted. All right. So let's talk about setting this up. I will get back to the summarizing the evidential analysis here in just a second. So ignore that, right? So the idea here is that now we're going to open up some data and we're going to explore that in this window here. So I've opened up the Harpo data set. Just very briefly, for those of you who want to follow along, you go to the hamburger menu, you go to open, and I am using the LSJ data set, the learning statistics with Jamovi. And this is a module that you can add here that'll add just a folder to your Jamovi folder. And then you can open up these data sets here, and they are all color coded. And I just opened up the Harpo data set because the Harpo data set from this set of creators is for independent samples t-test. And so that's why we want to open it here. So I opened that there. It's already open, so I'm not going to click on it. But you would click on it. It would open up a new window, and it will give you this information. Of course, I just have the data here, so ignore the results tab. Now, when you open this data set in Jamovi, grade here is listed as a nominal variable. And the reason why it's doing that is because it's reading integers, right? Because these are whole numbers. We don't want that to be a nominal variable. So I've gone ahead and I have gone to continuous. And so if you don't do that, if I click on the log ratio to take us back to the module here, if you don't do that, as you can see here, we've got the ruler telling us that's what our variable needs. You'll get an error up here right above the log ratio. And it'll say it can't handle two nominal data variables. And that's important because it cannot handle it cannot handle the nominal for the dependent variable. It has to be told that it is a continuous variable. So I'm going to go to grade, and I'm going to put that in my dependent variable. And tutor, if we go back to data, tutor is two different tutors in this statistics class. And we're trying to see which tutor produces the best statistic exam scores, right? Is it Anastasia or is it Bernadette? And this particular data set is all over my channel, especially the Jamovi videos on my channel. So is it Anna or Anastasia, or is it Bernadette? So go back to analysis, and we've got our log ratio here. So I'm going to put tutor, and don't worry that it says that it's a nominal variable with text-based. It can handle that, which is nice, right? It's just a grouping variable. It either needs to be nominal or ordinal, and because Jamovi can handle text, as long as they are spelled and capitalized the exact same way, case matters here, then they will be grouped into group 1, group 2, or group 0, group 1. It depends on how the R package handles that, but it's fine. It works. So here we go. Actually, I'm going to put that to 0, so it's the default. All right, so I put my dependent variables. We'll get to the outcome here in just a second. I just want to go through the settings and descriptives. So by default, the Welch's test for a t-test is selected. Now, if you're familiar with my other videos, Welch's is the correcting non-parametric test. It corrects degrees of freedom if you have unequal variance between your two groups. Now, student's t, or the regular parametric t-test, requires, it has the assumption that your two groups have equal variance. And if you know that you violate equal variance, then you have to use Welch's. Now, we're going to use Welch's regardless, because we can ignore the assumption of normality. We can just use the data as it exists, right? So we are going to use Welch's test, and you can't really do anything else. As you can see, you can't use student's t. So we're going to use that, Welch's, and it gives us the ability to put in our difference values for our null hypothesis, our alternative hypothesis, and our likelihood interval support level. And as you can see here, support interval for mean difference is another table here. So, and you can see S minus 2 likelihood interval. Now, 2 is put in here by default. I don't know why. I tried to see why in the package publication, but it is 2 by default. And the other value that I saw in the package write-up is 3. So you can use 2 or 3, 2 by default. You know, just if you know that the interval support level should be a different value, put it in there. I don't think it's useful to go any more than 3 as I was doing in my testing. So I wouldn't worry about that. I would just leave it at 2. The likelihood function is unchecked, but you can add that if you'd like. Okay. This is the likelihood function. It just shows you, it's just a graph of the likelihood function, the observed mean difference versus the likelihood ratio. Okay. Now we can have our descriptives. I'll talk about support intervals here in just a second too. I can add my descriptives plot in. This just gives you the mean, median, standard deviation, and standard error for my two groups, Anastasia and Bernadette, and as well as my N. And we can get a descriptives plot. It's going to put the descriptives plot just above the likelihood function with S minus 2 support interval, right? So the S minus 2 support interval works with the likelihood function, but here is just the descriptive plot. These are confidence intervals, and then we have a truncated y-axis, which isn't really all that great. All right. So let's go through the output here. So let's talk about the support table. The support table is giving you 3 rows. It's giving you the null hypothesis versus the observed means, the alternative hypothesis versus the observed means, and then the alternative versus the null hypothesis values, okay? Now, as you can see, I did not specify what my alternative hypothesis difference value is going to be. Leave it at 0. If this is something new that you've never seen before and you're not testing, or that you've never tested before, and you have no idea what the alternative mean difference is, don't leave it alone. Leave it alone. Now, if you know what your alternative hypothesis should be, maybe from previous literature, then you would put that value in there. I've seen this one before, and so after we go through this one, we'll go and change this to 5, and you'll see what the difference in this table looks like and what the resulting differences are in the output, okay? So let's just take the top row here, because the top and middle rows are the exact same, and they're going to tell you the exact same information, and that's because we had no idea what the alternative hypothesis should be, and so we know now. So the difference between Anastasia and Bernadette is that there's a difference of 5.48 in their means, right? 74.5 and 69.1. Nice. So we know that there's a difference of 5 statistical test score points between these two, right? Because those were the observed means, and HO was 0. Okay. Now the standard error of the difference is 2.69. That just comes from the variance in the observed. The variance and the N here. S is minus 2.73. S is minus 2.73. That is the log likelihood ratio test. Sometimes referred to as the Wilks test, but that's what S is. Okay, that's what S is. T, now T, this is Welch's T, don't forget, is 2.03. Okay, so these are not the same, so don't confuse them. So negative 2.73, and T is 2.03. Okay, the degrees of freedom is 23 for this t-test, okay? And that is 15 plus 18 minus 2, I believe, right? 25, 35, I don't know. The degrees of freedom is 23. And then here we have the p-value for the null hypothesis versus the observed means is 0.054. And if I went and did a t-test, an independent samples t-test, and I put this in, and we assumed normality, it would be around, P would be around this value here. And so this is the comparison for frequentists, okay? All right, so let's talk about support interval for mean difference. So this would be S minus 2 likelihood ratio. So S minus 2, we end up with a lower bound of 0.839 and an upper bound of 10.1 using the difference of 5.48, okay? Here are the group statistics, group descriptive statistics, excuse me. So let's talk about what these values mean, okay? And that's where the explanatory text comes in. This is amazing. So that's why I didn't really describe S and S minus 2 likelihood, because I know it was going to be down here. Okay, the analysis shows that there was moderate evidence, S equals negative 2.7. This is the absolute value. This table down here is absolute value, so don't worry about my negatives. Against HO versus observed means. Perfect. We can ignore the second one because this is just saying HA is the same difference. Because we didn't set our value here, we can ignore that one. And then there was no evidence either way, S equals 0 for HA versus HO, and that's because those two values are the same, okay? So we can kind of ignore that one. So we have S of 2.7, right? And so if we go down here, S of 2, or in between 2 and 3, we get moderate evidence there, right? Now, if it was over 3, and we were close to being over 3, there would be strong evidence, okay? The observed mean difference is 5.48, with an S minus 2 support interval from 0.839 to 10.1. There are no thresholds for S values, just guidelines on the strength of evidence for one hypothesis versus the other. They range from negative infinity to positive infinity, with 0 representing no evidence either way. Positive values are evidence for, while negative values are evidence against, okay? So if we go back up here, so the negative now means that there's evidence against HO, okay? So that means there is negative against HO being 0, or HO being the way the world is, or HO being true, the null hypothesis being true, for example. Okay, so we don't like that. That's great. Okay, the table below shows an interpretation of S values generally accepted in science. In contrast, UK law courts regard S of 4 as moderate evidence and 8.6 as strong evidence. UK law courts, that's wild. S values represent the weight of evidence and are additive across independent data. That's really cool. All right, support intervals. What do those mean? The log likelihood ratio interval identifies a supported range of values which are consistent with the observed statistic. In JEVA, it is denoted by S minus X, where X can be any number between 1 and 100. The S minus 2 interval is commonly used since it is numerically close to the 95% confidence interval. Okay, there we go. There we get our answer, is why you just leave 2 as the default. For the S minus 2 interval, it means that the values within the interval have likelihood ratios in the range of 0.135 to 7.38. corresponding to e to the negative 2 power and to e squared, or to the second power. Simply put, within an S minus 2 interval, no likelihoods are more than 7.38 times different from each other. Similarly, for the S minus 3 interval, likelihood ratios will range from 0.050 to 20.09, corresponding to e to the negative 3rd power to e cubed, and no likelihoods will be more than 20.09 times different from each other, okay? So here we have our likelihood ratio showing that with the S minus 2, and we can change that. I'm going to change that to 3 in just a second to show you the difference. One advantage of the evidential approach is that S quantifies the strength of evidence for or against the null hypothesis. Another advantage is that we can select hypothesis values that reflect our research interests. For example, we could choose a meaningful effect size HA to compare with any HO. This is shown by the last line of the main support table, where the p-value cannot be calculated. As data accumulates, the strength of evidence for one hypothesis over the other, another will tend to increase. Okay, so let me show you what happens when we change this to 3, okay? So we change that to 3, we get 2 different bounds for our difference. Nothing else in this table has changed, okay? Nothing else in this table has changed. Our S is still the same. And here we go is our log ratio. So if we go to 2, changes that slightly to 3. Let's go something big. Let's go 50, shall we? There you can see the line changes here. It's quite massive. Means with S50 support intervals. You can see that Anastasia, this doesn't make any sense, but Anastasia and Bernadette are somewhat equal here if we did that. So nothing changes about our S though. Our bounds, however, are quite huge. Now, if we change this to 1 and I scroll all the way down, you can see that we're up here by, what's that? Just below 0.4. And you can see that how close we got to 0 when we have that. And S1 intervals really shows the difference. Okay, really shows the difference. Again, nothing about S or our evidence changes at all. Nothing about that changes. It just changes what happens with the graphs in the output. Now, you would make a different you would use these values change. Everything else stays the same. All right, so let's change that back to 2, right? And you can see if we go back down here, this is like 0.1, so to speak. There's some overlap there with these S-2 intervals or confidence intervals. Okay, so let's change this. Let's imagine now that we've done this before, and we knew that Anastasia produces 5 better points than Bernadette on average. And so we're like, all right, there's a new set of data. We've got 5. Let's see what happens here, right? So that's a raw effect size there, right? That's the numerator of the effect size of Cohen's D. And we can see here that the table has changed. We've got HO, which hasn't really changed from what we already indicated, right? So there's a few little math changes here. So they did not round this to 7.3. Okay, they did not round this to 2.03. Right? Still 0.054 though. Now we look at HA versus the observed mean. So the value is 5 because that's what we put in, and our difference is 0.478, right? So we're only off by a half a point on the stats test on average, right? Standard error is the same, and so S is very close to 0 here. And so we've found it's still against. And I'll change it to 6 in just a second to change what that looks like. T, of course, 5, so a difference of 0.478 with a standard error of 2.69 is going to produce a non-significant T, okay? And you can see HA versus HO, right? Our null hypothesis versus our alternative hypothesis leaves us with an S of positive 2.7, which means that we are 2.7, yeah, 2.7, that's essentially 2.7, which means that we are going to accept HA rather than HO. Our alternative hypothesis has far more support than our null hypothesis. Our alternative hypothesis has far more support. So if we go back through the analysis, we have moderate evidence of S of negative 2.7. So negative is against the null hypothesis. Okay, so perfect. There was no evidence either way, S of negative 2.03 for HA against observed means, which is good because that means that our new set of data from our previous idea of 5, a difference of 5 on this statistics test between the two tutors. So we expected that and we got that, right? That's because we expected that and we got that. So that's check. So it's check, reject null, check. Alternative hypothesis was good. And then there was moderate evidence, S of positive 2.7 for HA against HO, right? So these two things confirm sort of our idea of this tutoring situation. Anastasia is better than Bernadette, okay? And again, we use this table to help us here, right? So our S of 2 doesn't change there, still 0.839 and 10.1, right? And here is the blue line here, which was 0 in the previous one, is now right there. And you can see that, oh, magnificent. So here's the dotted line is what the mean difference actually was. And then the blue line was our HA, and you can see how close we were to it. Now, let me show you what happens when we put in 5.48. Look at that. Blue line is directly over that, okay? And you can see here the HA versus observed means, literally the exact same thing. A p-value of 0.999 is literally 1, so it's exactly the same thing. So there you go. And that's what we have there. You can kind of see the black line, the black dashed line on that. But let's say if we put 6 here. And so, right, so the blue line now is on the other side of the dashed line. Oh boy, we've got an S of negative point, right? It's not positive anymore because we ended up going a little bit too far above. And yet our HA versus HO is still real good. And so that sort of shows you how this log likelihood using this ratio test uses sort of estimation and using these conventional ways to interpret S versus the likelihood ratio is helpful for determining how good our evidence is. And according to this, additive across independent data. So if we have one group that has S of 2.7, and then we have another sample, excuse me, I meant to say sample. If we have one sample, S of 2.7, and then we get another sample that gives us another S of 2.7, we have an S of 5.2-ish, 5.3, right? And so that's in between 4 and 7 here. Extremely strong evidence. Look at that. That's amazing. And if we get another sample, ends up being 2.7, that puts us over 7, more than 1,001. We get to say Anastasia is by far, over multiple classes, the better tutor than Bernadette. And so that's how you do that's how you use the JEVA. This has been a kind of a long video. The JEVA analysis package in Jamovi. If you have any comments, suggestions, feedback, anything that I did wrong, please let me know. Questions, all that kind of stuff, any kinds of comments, please leave that in the comment section down below. Don't forget, channel memberships are new to the channel in 2023. So if it's something that you can do and want to support the channel, please let me know. Otherwise, I appreciate the like, subscribing, and the commenting because that's what gets these videos discoverable. I'll see you in the next one. Thanks for watching. Bye.